All right, our next speaker is Professor Doug Hooton. Professor Hooton is a Professor Emeritus in the NSERC CAC Industrial Research Chair in Concrete Durability and Sustainability at the University of Toronto. He is also Principal at Concrete Durability Associates, Inc. His research involves finding ways to reduce the greenhouse gas emissions associated with concrete infrastructure. He investigates the use of materials such as supplementary cementitious materials and ground limestone and more efficient mix design to produce a stronger and more durable concrete product. His research has informed the specifications and codes associated with the American Concrete Institute, the Canadian Standards Association, and ASTM standards, where he chairs ACI C201 on durability, C130A on sustainable materials, ASTM C01 on cements, and CSA A23.1 on concrete. So welcome, Professor Hooton. Thank you for joining us.
Thanks, Sarika. Good afternoon. And I threw Larry Sutter on here, not to throw him under the bus, but up on the screen, because he and I have been working together on a lot of these changes at ASTM, both on the C1 and C9 side of those standards changes. So there's a standard path forward, and we want to know how we want to use less clinker and cement. The message has been there: less cement and concrete, less concrete in construction, to make changes in global warming. But how does ASTM help us get there? Or are we an impediment, or can we help with that cause? So we can replace clinker with content of cement using blended cements according to the ASTM standards, and we can use less cementitious materials. Optimized aggregate gradations are something that is not done very well in North America for the most part. It's allowed in C94 concrete spec, but not many companies take advantage of it except for the pavers. And we can optimize designs and use new mixtures. And as Mary talked about, there's new alternative SCMs on the market are coming out or being developed, and alternative cementitious materials. And there's specification development taking place, but there's a lot more to do. We're getting a lot more companies, such as these new development companies. At the last ASTM meeting in June in Denver, we had at least 6 startup companies show up saying, how can we get into the ASTM process? But some of them are producing alternative cements, some are producing supplementary cementitious materials, some of them maybe both. And so we're working on a strategy at ASTM to see how we can help get these people started in the ASTM process of getting specifications move forward. But first, what is a spec? A specification is part of a contract. It's a legal document. It's a purchaser agreement between the supplier and the purchaser of that product. And for materials, the basis, as I said, is a purchase agreement. And for construction, so typically specifications are part of a contract document for allowed construction. Specifications are not textbooks or research reports. They're a contract document for purchase. And you can't limit a property unless it can be measured. So we talk about performance and prescription. And one of the things we're doing is trying to move towards more performance-based specifications for materials. And that's why I've got this slide up there. Traditionally, a lot of the specifications have been prescriptive. So it has to be these materials and these proportions, as opposed to what are you trying to get out of the product? What are your performance parameters? Now, often they're a mix. If you look at ASTM C150, there's setting time requirements, strength requirements, but there's also compositional limits, for example. And it implies that all materials that meet those minimum limits in the standard are the same when they're prescriptive. So if we don't put the compositional limits in and we just specify performance, we can open up the doors a bit. We have a performance specification for hydraulic cements, C1157. It's been there since 1992. I think there's less than 5 states that have adopted it in the last 30 years. Because for some reason, people like to talk about performance, but they don't trust performance. Or they want to be the cooks in the kitchen, tell you how to make it as well. But as we move, just remember that if people think standards development is slow, it's a consensus-based process. It's not the same as many other parts of the world where you don't have consensus processes. So you've got many people coming from different viewpoints, and they all have to come together to agree on something together. And it changes roles and responsibility performance towards the engineering team. So they have to know what performance they're looking for, and often people haven't thought that through in detail. So we can meet a lot of the 2030 goals for reduction in global warming potential by just doing things that are allowed now in the standard. Without making any changes whatsoever, we can do these things. We have Portland limestone cements with up to 15% underground limestone that offer about a 10% reduction in CO2 just by utilizing them. They were intended to be equal performance to the base clinker for the type 1-2 cement they were replacing. They're not to be equal performance to every other cement. They were supposed to be equal in performance to the cement from the same clinker from the same factory. So if you're going to buy cement, some of the issues that have been evolving with Portland limestone cement, which seems to be unique to certain parts of this country and not other countries, is that people are buying multiple sources. It may not be there's issues, but like in Canada, we've been using Portland limestone cements. We're at 100% now. There was never any issue with adopting them and using them. The contractors did their base homework, and everybody communicated, and we got that done. Anyway, so 10% reduction from that. You can increase the level of SEMs. Fly ashes and slags have been used for years, but typically at lower replacement levels. A lot of DOTs limit the maximum SEM level to amounts that don't allow you to optimize and reduce further, but you're getting a direct reduction in proportion to what you're replacing with the clinker. And optimizing aggregations, I mentioned, if you just have a fine aggregate and a coarse aggregate, you're not optimizing your gradation. Most ready-mix plants or batch plants in North America use a fine aggregate and a coarse aggregate. The pavers often have an intermediate aggregate, which allows them to reduce their paste content, which is required for pavements. They don't get cracking and volume change, or reduces it. And in Europe and a lot of Asia, in the newer plants, they're using up to 6 different aggregate sizes and combining them to get optimized gradation, which could reduce the paste content, which will not only make more sustainable concrete, you get better quality concrete, because permeability of concrete is related to the paste fraction. The more paste you have, the higher the permeability for a given mix, and you're going to have more shrinkage and volume change because that's related to the paste fraction. So it's a low-hanging fruit that could save another 15% of the CO2 just by changing the cheapest thing in your mix, often is the aggregates. But it requires more bins at the ready-mix plants, and it requires a little more optimization work. So these are all allowed, and they're allowed in the building code. The 318 building code allows them already. They're allowed in the Canadian American specs, and they can be done simultaneously. You can easily get a 50% reduction or more in GWP just by doing things we can do now without doing anything new. For example, C595, the blended cement spec, that's where the type 1L cements ended up. There's also a type 1T, which is limestone plus an SEM, such as fly ash or slag, which allows you to blend these materials. And as I said, C94 allows optimized aggregate gradations. Last month, apparently, Portland limestone cement is now 54% of U.S. production of cement type. And right now, like I say, in certain Ontario, I can't speak for the whole of Canada, it's 100%. All concrete contains SEMs pretty much, but like I said, some of them are restricted by prescriptive agency specifications, which are often legacy type specifications. And not many people do the aggregate optimization. So it's fairly easy. As I mentioned, this is just a cartoon from the Cement Association of Canada report. Just using a limestone cement with either a moderate amount of fly ash or slag, you can get down in the 50% reduction range. Now, Mary mentioned this earlier. What's the availability of materials? And this is something that Karen Scrivener at EPFL has been pushing, is that on a global scale, when we're trying to make an impact, fly ash and slag are relatively small availability in proportion to the Portland cement that's being produced. A lot of that Portland cement, about 50% of that is from China, the Portland cement. So, and China seems to have peaked now, but India is growing. They're probably going to double their cement production in the next decade. And Africa is rapidly developing as well. So what's available for these people if we're not going to have more coal-burning power plants, and the blast furnaces are being converted into electric arc furnaces, so the amount of that blast furnace slag will reduce in availability over time. And you can do all these things. People talk, we have I'll talk about these other standards, they're relatively small proportions. So what's available is raw limestone and clay that can be calcined. It doesn't have to be high-quality clay, just can be calcined and blended together, and you can replace, as Mary showed, 50% of the cement, and this is the same graphic she showed, 50% less clinker, about 40% less CO2, just using a different pozzolan. A calcined clay is already allowed. It's already been used in concrete in North America, but typically the high-purity metacolins. Now there's companies making these lower-grade. I think Ash Grove has a plant now in Nebraska, and I understand that Holcim is doing that in Utah now, calcining clays. And then they can blend that with the limestone cement and make a 1T cement that is allowed now under the standards on 595. And you can get similar strength performance, better resistance to ingress, and resistance to other types of degradation mechanisms. And you don't need the high purity material. You can use the stuff that the China clay people in the pharmaceutical industry clays throw away as waste, as the raw material. So where are the standards barriers with something like that? Because there's been a lot of play about LC3. Everybody's excited about it. I get calls saying, where can I get some LC3? And the point is right now you can't. But it's happening fairly quickly in various parts of the world. They seem to have good properties. The availability is good, which is why it's great, especially in the developing part of the world. India and Africa have a lot of clay materials, more clay than limestone. So there's some opportunities there. Currently, the standards allow cements with up to 15% limestone that can be used together with an SEM. So you could essentially make an LC3 today under the current standards. We wouldn't have to change anything. But while a lot of the DOTs have adopted 1L cements, they haven't adopted 1T cements. They say 595 1L cements, but they don't adopt 595 blanket. Now, the 1157 performance spec, as I've mentioned, been there for the last 30 years, would allow all these things because there's no compositional requirements. You just measure performance, but people aren't speccing it. So there's some limitations there. So we need to learn how to use performance specifications. We either trust performance or we don't. And this is the 1157 scope. Performance spec covers hydraulic cements for both general and special applications. There's no restrictions on composition of the cement or its constituents. You just define what's the performance you're looking for, setting time, strength, volume, stability, those things. And you'd think people would use this, but they don't. As I said, only very few people have adopted it. People want performance, but for some reason they also want to know what's in it. But he's a chef. This guy wants more sand in his mix. And so a lot of the stuff on prescriptive is because of legacy specifications that have been developed over 100 years before the use of SEMs, just based on Portland cement, water, and aggregates. They have not considered the fact that concrete technologies moved on with SEMs and chemical admixtures of various types that can drive performance. So we're developing new tests, but some of the things people don't understand or don't want to take on. So performance specifications require performance tests. Many rely on prescriptive tests. Some are pretty old. Tests need to be practical to be in a spec because you want to do them in a reasonable time frame. And we need to correlate with field performance, as Mary mentioned, and it takes time. And we need reproducibility and accurate test methods. So, I mean, I'm playing up to the ASTM part of this story, why it takes some time to do this. And we've got to have consistent product. You can use any product in concrete as long as it doesn't change every day. It's got to be consistent. And so we need some data on consistency. So we've had some recent successes, though, and Mary mentioned harvested fly ash. I was involved with getting the standard changed in North America, Canada, and the U.S. on allowing harvested coal ash, because the number of coal plants has significantly reduced. But there's almost 2 billion tons of coal ash in landfills around the United States at over 500 sites. Now, some of it's pure fly ash, some of it's intermingled with bottom ash, but it can all be processed. It's exactly the same material. Now, Mary mentioned that some of it was waste. wasn't used because it was not quality. That's not the case in 90% of the cases. The stuff is, there was just no market for it at the time it was put in the landfill. They were producing more ash than there was a market for. So a lot of the stuff in the landfill is actually better quality than a lot of the existing plants are producing now because of the environmental controls that have been put on coal-fired power plants over the last 20 years. Low NOx burners, low SOx requirements, and mercury scrubbing. So a lot of the ash in the landfills is better quality to start with. You just have to get it out of the ground and process it to reduce the moisture and de-agglomerate it. And companies have been doing that, and now the specs allow it. Since June of last year, that's been allowed. One of the issues with new materials that are coming on the market, alternative SCMs or different SCMs, is what are the reactivity? How do you tell? A lot of the specs we have, like 618 for fly ash and natural pozzolans, uses a strength activity test that, although it's okay with fly ash because we have a history of using fly ash, we sort of know what it does. I can take ground sand and make it pass the strength activity test in 618. That's not a very ringing endorsement for endorsing the reactivity of it. So we developed a reactivity test as part of a RILAM committee I was involved with, and I championed this through the ASTM system to get this reactivity test, the so-called R3 tests, using isothermal calorimetry as one method and just bound water measurements as another, to evaluate whether pozzolans are actually reacting, and we have a standard for it, which we're hoping to incorporate in a performance spec for SCMs. We got the ground glass pozzolan standard in 2020, which allows municipal waste glass recycling operations to process and grind the glass and make it into a pozzolan. There's about, I think, 3 or 4 plants in the U.S. operating now, but the total capacity is still under 1 million tons, so it's not a huge quantity. And there are some issues with using it in terms of its high alkali content, in terms of ASR issues. One of the things we need is better performance tests, and something that has been developed with a number of people, and Larry Sutter got this through the system, was a foam index test. It's not a new test, but it was originally applied to evaluate loss in ignition and fly ashes, but it can be, I chair a committee on performance of cementitious systems with chemical admixtures, like looking at the whole binder, and this test can be used to evaluate whether you're going to have air entraining issues with a system of combination of your chemical admixtures and cementitious materials. And it's a quick and dirty test. You can find out whether you potentially have issues and how much extra air entrainer you might have to add to get the air content you're looking for without waiting to put it in a truck and discover you don't have the air content. So it's a test that is a predictive test. There's a brand new standard that just came out in the last couple of months, cements that's set by carbonation, to allow some of the materials that they don't hydrate, they set by carbonation. So they sequester carbon. There are a couple of companies out there, such as Solidia, that use that, use a wlastonite type of calcium silicate that you then, the CO2, it binds with CO2. It doesn't harden on its own. It hardens with the presence of CO2. And there's some other companies taking advantage of that too. There was a Carboclave up in Montreal making masonry units with waste steel slag, just basically taking steel slag, making it into masonry units and carbonating it to get it to harden. It meets all the specs. And there's a test method that goes with that that's been developed to go with that spec to evaluate how you measure the strength, whether it's going to get hard or not, and how strong it's going to get. So it's tied into that specification. So that's all happened in the last couple of months. There's a test for just came out as well this year on strength of alkali-activated cementitious systems. Again, for the cement side, basically using the same 2-inch cubes that people use for other acceptance tests, but it's been modified to allow them to test these alkali-activated systems. There's a lot of things that still need to be done. We were just talking about colloidal silica today in the hallway, sorry. We're working to develop, to modify existing standard, C1910M is for blended SCM. So you could take a fly ash and a slag or a different pozzolan, 2 different materials, put them together and meet it. But right now it says each one of those individual materials in your blend has to meet a standard on its own. So if you had a fly ash that didn't meet one requirement, say the fineness or loss in ignition, you couldn't use it in that standard as a blend. We're trying to change that, open it up so the final product meets the spec, not the individual ingredients. And that will open it up to more accessible use of a number of materials. We're trying to look at composite cements under 595. We're also looking at a performance spec for supplementary cementitious materials. And again, I'm trying to use this reactivity test we talked about, the foam index test, some of these things to evaluate these new materials as a performance evaluation of these new materials as opposed to saying what's in it compositionally. And well, that was the one I mentioned before about each one of the raw materials in that spec has to be ASTM compliant on its own, and that causes some restrictions on evaluating materials that could be used. And one of the issues, that would also be an issue if you're trying to make a blended limestone clay system, like what I would call an LC2, to replace 50% of your clinker with a blend of limestone and clay. Right now, that would not be allowed under this spec because limestone isn't defined as a supplementary cementitious material. And that is an impediment. We want to fix that so it would allow, because blended cements have been big in Europe and other parts of the world as single products. That's not been the history here in North America with ready-mix plants doing SCMs on this as a separate addition at the ready-mix plant or at the precast plant. And having an LC2 spec would allow them to do the same thing as LC3, but added separately at the ready-mix plant. So we need to make a change that would allow that to happen. So we're looking at that as well. As I mentioned, there's many new startup companies with new materials coming in. They're coming to the meetings because they realize they need to fit into specifications to be used, especially for building code applications. The building code applications have to recognize the materials by standards that are specifications. And they may have to look at modifying existing test methods because a lot of test methods we have were designed for Portland cement concretes. You can say, well, we could do the same test, but you may have to modify the test. So we have to figure what needs to be modified to allow these materials to be tested to meet a specification. Like I said, we did that for the alkali activated system, the strength system, and the carbonation cement system. So we need to do that, find out what these materials are, how would we have to modify it to allow them to get into the spec, and that's where we're headed. But one of the also things I'm just going to mention is these new materials have to fit into the existing infrastructure. The concrete industry, you have ready-mix plants, precast plants, you've got to be able to transport the material into a plant, put it through a mixing plant, put it into transportation units such as ready-mix trucks, and place it at a job site. So that infrastructure exists, and nobody's going to build a new infrastructure for a material that doesn't fit that bill. So it has to fit into that existing infrastructure for all that part of the system. And some of the new startups, they're great, interesting products developed by bright people, but they haven't thought that through. And that became apparent last year in the Min Road test site that Larry Sutter helped organize, where they, on I-35 south of Minneapolis, they placed test sections on the interstate. And some of the materials, one of them couldn't get out of the tote bags into the ready mix. One of them started to set up in the ready mix. One of them started to set up as they were trying to place it, so they had to rip it up with it, because these people had never tested it in practice in the field. They'd only ever done it in the lab or in small scale, so they hadn't taken it through the system, scaled it up to the applications and things that happen in the field. So we want to accommodate people, but they've got to, the people developing these products have to realize they have to fit into the existing infrastructure to be able to be used in that. So we're trying to evolve the standards as fast as we can, and we're trying to respond to needs of the community as they change. But there's always resistance to change. We never see resistance to change here, do we? And it doesn't matter, and if you have a new product and something goes wrong, everything gets blamed on the new product. I've seen it 4 or 5 times with changes in materials over my career. You always blame the new material for anything that ever went wrong. It doesn't matter what the reason is. The new material gets blamed because it's easy to point to. So we need to make changes. There's only a few of us working in this space. One of the things, I'm a recovering academic, and as is Larry, but there's very few academics show up at ASTM on our cement and concrete committees because they find it boring. It's not exciting. It's not research in the lab doing students. It's taking the process through to something that can be used commercially. And they usually lose interest after a couple of meetings because it seems pedantic and boring. But it's a basis of trade and contract agreements, so that's important if you want to see your product used. So thanks for that. We're working like beavers as fast as we can, and we welcome your participation in that process. Thank you.